All right. Ready to dive into some geometry.
Always. What shape are we tackling today?
Today we're going deep, deep into the world of triangles.
Triangles. Really?
Yeah.
Everyone knows about triangles, right? 3 sides, 3 angles?
You'd think so, but trust me, there's more to these guys than meets the eye.
Okay, I'm intrigued. You've definitely piqued my curiosity.
We're talking about the kind of stuff that blew my mind when I was digging through our source material for this deep dive. Like, did you know that just by knowing the lengths of a triangle's sides,
Just the sides?
yeah, just the sides, you can figure out exactly what shape that triangle has to be?
Huh. I guess I never thought about it like that.
It's true. It's like a hidden code. And speaking of codes, that brings us to the concept of congruent triangles.
Congruent triangle. So 2 triangles that are exactly the same.
Exactly. They're like identical twins of the triangle world.
But don't they have to be, like, the same size and everything to be congruent?
That's the thing. It's not enough to just look at them. There's a whole detective process to prove those triangles are actually congruent, and it's all laid out in the source material.
So there's specific rules you got to follow.
You got it. You can't just eyeball it. Imagine building something like a roof truss. You need those triangular supports to be exactly the same, or the whole structure could be wonky.
Makes sense. So how do we know for sure? What are these rules?
Well, one of them is called SAS, which stands for side angle side.
Side angle side. So 2 sides and an angle have to be the same.
Almost. It's 2 sides and the angle between those sides. And if those match up between 2 triangles, boom, they're congruent.
So it's not just any 2 sides and any old angle. It's
Yeah.
got to be that specific arrangement.
Exactly. And our source material actually has some really cool diagrams showing why this matters. Like, if you have 2 sides that are the same length, but the angle isn't sandwiched between them.
You could end up with totally different triangles.
Exactly. So SAS is all about that specific combo. But there are other ways to crack this code too, right?
There are. Like what? Give me another triangle code.
Well, how about ASA? That's angle side angle.
Angle side angle. So that's like the opposite of SAS.
Exactly. Instead of 2 sides and the included angle, you're looking for 2 angles and the sides sandwiched between them.
Got it. Match those up,
Hmm.
and you've got yourself a pair of congruent triangles. Okay. What about if you only know about the sides? Does that tell you anything?
You read my mind. That's where the SSS rule comes in. Side, side, side.
Okay, that one seems pretty straightforward. If all 3 sides of one triangle are equal to the corresponding sides of another triangle, they gotta be congruent,
You
right?
got it. It's like the sides dictate the whole shape of the triangle.
Okay.
And get this principle, this SSS rule.
It's not just some theoretical thing, is it?
Nope. It's used all the time in the real world. Engineering, architecture. Think about designing a bridge. Those triangular supports need to be exactly congruent for the whole thing to be stable.
Wow, I never realized how important these rules actually are.
Right, so we've got SAS, ASA, SSS, all these ways to confirm if 2 triangles are truly identical. But I'm guessing there are times when triangles are, like, almost the same, but not quite.
Right, like they have some things in common but aren't a perfect match.
Exactly. What about those cases? What does our source material have to say about that?
You're spot on. Not every triangle gets to be part of a perfectly congruent pair.
There are, like, triangle singles out there.
Well, not exactly, but it's true that not all triangles are created equal. Or should I say, perfectly congruent.
Okay, so we're talking about triangles that are kind of similar but not identical twins.
Exactly. Think of it like a scale model of a building. The model and the real building, they might have the same shape.
But totally different sizes.
Exactly. And in geometry, we call those similar triangles.
Right, similar triangles. I remember learning about those vaguely. It's all coming back to me now.
Well, similar triangles, they're a big deal. They have all the same angle measurements, but their sides,
They're not the same length, but
they're proportional.
proportional, meaning
Meaning the sides have the same ratio to each other. Like one triangle might be twice as big as the other, so all its sides are double the length.
Okay, I'm with you. But why does that matter? Is that another one of those geometry things that sounds cool but doesn't really have a real-world use?
Not at all. Remember those real-world connections we love to point out? Similar triangles. They're all over that. Imagine you need to measure the height of something really tall.
Like a tree.
Exactly. A tree. You wouldn't believe how useful similar triangles are for that. You can figure out the tree's height without ever leaving the ground.
No way. Seriously.
Yep, just by using a little similar triangle magic.
See, I knew there was a reason I love geometry. It's like having a secret toolkit for understanding the world.
It absolutely is. And that reminds me, our source material dives into some other really fascinating triangle properties too.
Oh, like what?
Well, how about a little something called an isosceles triangle?
Isosceles. That's the one with two equal sides, right?
You got it. Two equal sides, two equal angles.
Wait, the angles are equal too? I just thought it was the sides.
That's the beauty of it. The source material actually lays out this really elegant proof showing that in any isosceles triangle, the angles opposite those equal sides, they're always equal too.
So it's not a coincidence. It's like a rule.
It's a fundamental property of isosceles triangles. It's amazing how much symmetry is packed into this one shape, right?
It's true. They've always seemed kind of elegant to me. Now I know why.
And speaking of elegance, the source material also talks about something called the triangle inequality theorem.
Triangle inequality theorem. That sounds intense.
It's actually pretty intuitive once you wrap your head around it. Basically, it says that you can't just slap any three sides together and call it a triangle.
What do you mean?
Well, the rule is that the sum of any two sides of a triangle has to be greater than the length of the third side.
Okay, that actually makes sense when you put it that way. Like, if you had one side that was super long,
And two really short sides.
yeah, there's no way you'd be able to connect them to make a triangle.
Precisely. The triangle inequality theorem, it keeps things in check. It sets boundaries for what kinds of triangles are actually possible.
It's like a rule that even triangles have to follow.
Exactly. Rules even triangles have to follow. So we've got congruent triangles, we've got similar triangles, we've got isosceles triangles and their special properties.
And who could forget the triangle inequality theorem? I'm starting to feel like I could write a book on all this.
You might just be able to. But we've still got more ground to cover. What other secrets do these three-sided wonders hold? Plenty more. Triangles are full of surprises.
So where do we go from here? What haven't we uncovered yet?
Well, we've talked about congruent triangles, those identical twins,
Yeah.
and we've touched on similar triangles.
The ones that are like scale models of each other.
Exactly. But there's one more rule for congruence that I think you'll find interesting.
Oh, another rule. Lay it on me.
This one's specifically for right triangles. It's called RHS.
RHS. Okay, what does that stand for?
Right angle hypotenuse side.
Right angle hypotenuse side. So we're talking about those triangles where one angle is always 90 degrees.
Exactly. And the hypotenuse, that's the longest side, right across from that right angle.
Right. So what's the side part?
It means that if you've got two right triangles and their hypotenuses are equal,
Okay, their longest sides match up.
and one of the other sides is equal to, then boom, those triangles are congruent.
So just knowing the hypotenuse in one leg is enough. For right triangles, at least.
Exactly. It's like a shortcut for proving congruence, just for those special right triangles.
That's pretty cool. So if you were like building something and needed to make sure you had a perfect right angle.
You could use this rule to double-check your work.
Exactly. It's like a little geometry hack.
And our source material actually talks about how this principle is used all the time in construction.
Really?
Yeah, to make sure corners are perfectly square.
That makes so much sense. And to think all this time, I just thought triangles were, shapes.
They are shapes. But they're also so much more than that.
It's like we've uncovered this hidden language. Triangles, they're the key to understanding everything from architecture to engineering to who knows what else.
Exactly. And that's the beauty of geometry. It's all around us, just waiting to be discovered.
This deep dive has been amazing. We've covered so much ground, from those rules for congruence to those special properties of isosceles triangles and, of course,
The triangle inequality theorem.
how could we forget? I feel like my brain is bursting with all these new triangle facts.
It's a lot to take in. But the takeaway is that these aren't just abstract ideas. Triangles are everywhere, and understanding their properties.
It gives you this whole new perspective on the world around you.
Exactly.
So, to our listeners, keep your eyes peeled for those three-sided wonders. You never know where you might spot a triangle putting its amazing properties to work.
And until next time, keep exploring those geometric mysteries.
We'll be back to uncover more secrets of the shape world.